Hey everyone. Thank you so much for joining us today at the Open Lakehouse Meetup, organized by Cloudera and the Oleg team. I'm super excited to see the crowd here, and thank you so much for taking the time on a Saturday, to join us at this amazing meetup. And we have a lot of exciting talks, lined up for you today. So I'm sure this should be really beneficial, overall for your work or your personal interest. So my talk would be about Apache Iceberg, the key innovations so far, and what's coming up next in the upcoming version. So it will be like a technical evolution journey of how we started with Iceberg, what new capabilities that we introduced, and what are we looking at in the next phase for Iceberg. So with that, let's get started. A little bit about me. My name is Dipankar. I am the Director of Developer Relations at Cloudera. I joined like 4 or 5 months back. Previously, I was with companies like Dremio, OneHouse, and Click, and most of my experiences with the Lakehouse has been for the past 4 or 5 years, where I was primarily involved with Apache Iceberg, Apache Hoodie, Apache Stable, and Arrow, and all of this open source projects. Um, and it's really interesting for me to see the community of Iceberg grow to the point that we see now, right? I remember back in the early days, we used to go around hallways and conferences tracks and speak about Iceberg. And people were like, why do I need something like Iceberg, right? I mean, we have something like a data warehouse or data lake. What is the value of Iceberg? So we really spend a lot of time in explaining engineers the value that something like an open table format can bring. And the picture has changed a lot now, right? I mean, most of the data warehouse vendors or other ecosystem vendors, they have adopted Iceberg, which shows the community growth, which shows the openness part of that. And that gives me a lot of enthusiasm and pleasure, that I was part of the smaller, effort that we made initially. I was also lucky enough to produce some of the foundational educational materials around Lakehouse and Iceberg. I published a research paper very early on about the data lakehouse architecture, how it compares to a data warehouse and sorts. I co-authored the first book on Iceberg, which is the Apache Iceberg, the definitive guide, the version 1 of it, and then I am also super excited to announce the release of my upcoming book, which actually it should be published like next week or so, which is called Engineering Lakehouses with Open Table Formats. So really going into all of these different table formats, the internals of it should be a key aspect of that as well. And if you're interested in kind of buying or understanding and reading the book, there's a QR code. Feel free to scan that and let me know if you have any questions as such as well. So with that, let's dive into our talk today, which is, let's see how we have evolved through this journey, right? So I'm sure a lot of you here have worked with data lakehouses now until, at this point of time. So I'm not going to take a lot of time in this particular slide, but, we started with the overall idea of like organizations needed to build centralized, reliable, and scalable data platform, right? So data warehouse were kind of the first one that enabled to deal with this. It kind of was the centralized repository, if you may. But it struggled with unstructured data or kind of semi-structured data at that point of time, specifically for cases like machine learning. So then came the era of the data lakes with the Hadoop ecosystem, and data lakes were kind of great, right? Organizations could basically store all of this data, whether it's structured, unstructured, semi-structured, didn't really matter. And again, with the rise of cloud and its cheaper price, we have the cloud data lake storages now, like Amazon S3, Azure Blob. So you can basically scale out your storage as you would like, right? But obviously, there were some problems with data lakes, and you just can't dump all of your data. There was no governance, there was no data quality checks. Most importantly, there were no atomicity and consistency guarantees with transactions. So, if you do things like multiple concurrent writes, you didn't have those guarantees whether those writes were successful. It might be partial. And also, like I said, there is no data quality or governance. So there is no, it's hard to make sense of all of that data. So that gave rise to this newer architectural form or paradigm called data lakehouse, which in a way combines the best of the both. And when I say best of the both, I mean like you take the data management capabilities of a data warehouse and the cost and scalability perspectives of our data lake, and that gives you a data lakehouse in a more simpler term. All right, so diving straight into Iceberg, right? Iceberg came out of Netflix, and I'll talk a little bit about things from the context. So if we take a step back, most early big data workloads were built on Apache Hive tables, right? That were running on HDFS. Now that design worked well at the time. Hive kind of defined a table using a directory-based structure, and partitions were mapped to folders, and then there were files inside of them, right? So on HDFS, this worked out really great. But over time, Hive table format showed some of the limitations, especially at Netflix scale. Um, and more importantly, as Netflix were kind of moving from on-premise to cloud object stores like Amazon S3, right? So S3 is fundamentally different. It stores objects in a flat namespace, and directory structures are really just prefixes. So listing millions of objects across deeply nested Hive partitions, that became slow and expensive, right? On top of that, S3 also applies this request rate limit at the prefix level. And in a typical Hive layout where many partitions, they share a common prefix, concurrent listings or writes can easily hit those throttling limits. And ultimately, that's why you see errors like you see in the screenshot here, like 503 or 5050 and those kind of errors. And this wasn't just a performance issue, right? There were deeper problems around concurrency. For example, multiple writers corrupting the table state. Statistics were stale. Sometimes you will end up with partial writes and inconsistent views of the data. And all of this motivated a fresh rethink of how tables should be defined on the object storage, right? So Iceberg emerged from this with a very few clear design goals. One is, you should ensure table correctness and consistency, even with concurrent writers. Number two, enable faster query planning without relying on full directory scan, which is expensive. Three, allow users to think in terms of logical tables and not physical file layout. And finally, support safe schema and table evolution at the cloud scale. So Iceberg response to the limitation of this Hive style table were fundamentally to redefine what a table meant on object store, cloud object store, I mean, right? So instead of treating all the files under a directory as a table, Iceberg actually introduced the concept of canonical list of data file, which were tracked explicitly through the metadata, that is the manifest and the snapshot, right? So in other words, the table is no longer inferred from the file system layout, it is defined by the metadata. So that meant the readers, they don't discover data by scanning data directories anymore, right? They read a snapshot that tells them which data file belonged to the table at that point of time, right? So there is no expensive directory listing, and that makes query planning more predictable on object storage. Now, each commit, you probably know this, each commit in Iceberg produces a new snapshot representing a complete immutable view of the table at a specific moment of time, right? So writers, either they successfully publish a new snapshot or they don't, right? There is no partial table state. And the readers, they always see a consistent snapshot even while the new data is being written, which is what enables this atomic commits and snapshot isolation guarantees, right? So by separating the logical definition of a table from the physical layout of files, Iceberg made it possible to reason about the table state and evolve tables over time, right? Most importantly, at cloud scale. So before we go any further, it's important to be very clear about what Iceberg is and what it is not. And this context matters because historically, like when I mention someone like Hive, the Hive term has become quite nebulous, and it means different things to different people. Some things of it as a query engine, some as a meta store. But for Iceberg is a table format specification, right? And that specification defines how the table data and metadata are laid out, how the bytes of the storage represent a table, its snapshot, and its evolution over time. And alongside the specification, obviously, Iceberg provides a set of libraries and APIs, and compute engines like Spark, Trino, Flink. They use these libraries to read and write Iceberg table correctly, right? So they don't invent their own semantics. They follow the rule that are defined by the specification. And of course, it's not a storage engine or a compute engine, and that separation is intentional. Iceberg's open version table specification, it makes sure that capabilities are not tied to any single engine or vendor, right? It's an open table format separated from the storage engine or the compute engine. So different engines can evolve independently, that's fine, while a table remains consistent and correct, right? And that brings us to the core of today's talk. That is, Iceberg has evolved through the specific versions, V1, V2, and now we have V3, and we are also thinking about the upcoming V4 version. So I want to take a little bit through the journey of this evolution, right? And how we started this in first place. So people who are completely new to Iceberg, you should have a clear picture of how we started and how we are evolving as a format, as an industry today in the Lakehouse space. So this is the first Iceberg specification, the V1. Of course, everyone has seen this particular architectural diagram. The first problem for Iceberg to solve was how do we get this database like semantics and all this ACID guarantees, concurrency control and stuff
on the data lake, specifically at the cloud scale, right? So basically, to do this, Iceberg introduced this multi-layer architecture form, and at the bottom you have the data files. Those are managed by the manifest file. They also keep a track of all the statistical information, information with things like partition information. Then you have the manifest list, which acts in some form like an index, if you may. Basically, Compute Engine do not have to read all the manifests. You can just look at the manifest list and find out which manifest file makes sense for the query, and get your data. And then you have the metadata file, which actually has the current snapshot reference. But most importantly, it keeps a track of the table information, the schema information, and all this like metadata that you need for the tables. And on top of that, you have the catalog. Now, catalog is not technically part of the specification itself. It's something super important for Iceberg, because the way the Iceberg maintains those ACID guarantees is via this catalog thing, right? So every time a compute engine makes a commit to Iceberg, the new metadata file is being referenced in that particular catalog, and that is done more atomically, right? That swap happens more atomically. So that means you have those guarantees with optimistic concurrency control and stuff. So writers, they don't modify existing metadata, they create a new version of the metadata, right? And that's important because that means we have a stable and immutable version of that snapshot at that point of time. And the spec one also brought in things like schema evolution and things like that. So columns can be added, renamed, or deleted as you would like to without writing your existing set of data files. So that's the important part. So like I said, that the decoupling of the logical and the physical schema helps a lot with that part, because you're talking to the metadata now and you're not really talking with the data files itself directly. And through releases up to version 11.0, V1 actually became the default, and that's when the V2 came into the picture as well. So by the time Iceberg reached version 11.1.11.1, the community approved the spec V2, and this was a major inflection point as well. So spec V1 had solved the correctness and the snapshot isolation issue. Now we were thinking about, okay, how do I make my data lakehouse more mutable, right? And how do we do things like, for example, record level updates, right? For example, for things like CDC, incremental processing, and more of like, late arriving data backfills and stuff. So that was the second goal of the V2, right? And initially, these mutations were using a copy on write approach. So the idea with a copy on write approach is that every time you change a record in a particular Parquet file, which is immutable in nature, Iceberg has to create a newer version of that, right? So that means the write amplification is super high, and you're bearing a lot of costs in that process, right? Now imagine doing that at scale, right? It can be a lot of overhead, cost, performance benefit, you're losing that a lot. So we thought that, okay, let's think about this from a different perspective. And I personally feel like Iceberg also looked at these things from like other table formats like Hoodie and Delta Lake as well, but they introduced the concept of a delete file. So now, instead of rewriting that entire Parquet file, we are putting all of these change records in a different file, which is the delete file. And at the query time, it's the responsibility of the engine to merge that particular delete file with the data file. And that's how we came up with the merge on read approach, right? So you're merging on reading versus kind of copying on writing. So that's the true distinction. So by introducing this delete file instead of rewriting the existing data file, Iceberg kind of like tackle and enable like us to do things like more streaming-based writes, more low latency-based writes, right? And that reduced the write amplification by a lot. So by the time Iceberg reached version 1.4.0, V2 actually became the default. So we had actually spent a lot of time in the version 2 and how we evolved from the version 1, right? So we became from more append-only mutable workloads, to append-only workloads to more mutable workloads from version 1 to version 2. That was kind of the distinction between the two versions. All right, so now we are in V3, and Iceberg adoption obviously, grew. Like, so the workloads of course, like they will come, and we can see that more diversified workloads now, right? So now we're dealing with things like semi-structured inputs, like spatial, geospatial data, streaming pipelines, and all of these different sort of things, right? So spec V3 is where the community tackled this broader setup problem, right? So the first wave of V3 capabilities appeared in 1.8.0 version, where we introduced something called binary deletion vector. Again, I think deletion vector was pretty much omnipresent in like Delta ecosystem, but this is something very much required. I'm going to talk a little bit more about how that benefits us in the later slide. But there are other things like, for example, the introduction of the variant data type, which was, very much necessary for kind of like JSON, like kind of semi-structured workloads as well. And then we introduced more geospatial type workloads for more event-based thing, like nanosecond precision timestamps. And then in version 1.9.0 and 10.0, Iceberg introduced these things called row lineage mapping tracking, which is another key feature. I think has been a great enabler as well. And we can see those workloads coming in now. And there are other things like multi-argument transformation and encryption schemes and stuff. So let's start with a major area. So this is the slide where we're talking about this feature itself. I want to take a little bit of time understanding how these features make sense in the real world use cases, right? That's super important. So the first area was mostly incremental processing and CDC kind of workloads. So until recently, Iceberg, dealing with streaming workloads was kind of a pain in a way, if you may. Because data files are immutable, pipelines had no reliable way to like understand how or what actually changed between the two data files, right? So as a result of that, either we have to rescan that entire partition or build custom like differentiation logic. So think about things like all the ad hoc joins you do, all the scans and the state tracking that you had to do outside of the Iceberg ecosystem. So more of like custom logic, right? So, and these were very expensive, right? These were very brittle. Like if you had to change something, it was very hard to do that. So Spec V3 fundamentally changes this by introducing this row lineage tracking. So what happens is Iceberg now assigns each row a persistent identity across the column, right? So they have introduced a field called like the metadata, the row ID and the sequence number that allows you to keep a track of what has changed at a row level between two snapshots, right? So with these fields in place, engines can now precisely detect what rows change between these different kind of snapshot, not just which files or partition change. So for developers, this is a direct and practical impact, right? One, CDC becomes simpler in a way because pipelines can now consume only the changed rows. Materialized views refreshes now no longer require a complete refresh and stuff. And downstream incremental processing becomes a little bit easier because imagine you have to reprocess this entire volume of data that you had in your data lake, right? Without knowing what has changed. Uber is a great example as that. You know, they were implementing Hoodie, and every time they were making some updates, for example, with the trips, let's say, late arriving payment data and stuff, they had to actually reprocess the entire data just to make sure those updates were reflected. So this is the same idea we are trying to achieve with Iceberg now. So you basically ask Iceberg, hey, give me the change sets between the two different snapshots, and I can make a sense of that and build a pipeline based on that. The next in the spec V2 we saw was basically the external delete file we talked about, right? So the delete files had enabled us to kind of tackle that write amplification problem, right, at the first place. But now we are in a different problem because imagine in practice, delete files tends to accumulate over time, right? You will have a lot of delete files, especially when you're talking about mutation heavy tables where you have a lot of workloads running for low latency based write. Imagine you're writing for more streaming based pipelines and stuff, right? So many engine, and actually this is today valid as well, they do not compact this delete file automatically. And Iceberg does not have a service in its own that can actually do this compaction automatically, right? So it's still dependent on the compute engine part, right? So that means we ended up with dozens of delete files that are associated with a single data file. And imagine at scale, you will have a lot of data files. That means a lot of deletion files as well. So this means all the engines at the read time, they had to merge all of these different delete file, which can be pretty expensive at scale as well, right? So to deal with this, we introduced something called binary deletion vector. So instead of representing deletes as delete file, what we do now, we encode this deleted row as compacted bitmaps, and we kind of link that particular bit position to a corresponding row position, right? As you can see in this image here. This is not a direct representation, but in a way, it should provide some idea of how that is maintained. So what this design brings is that it eliminates the need to manage large number of external delete file, which simplifies the table maintenance. As you would know, table maintenance is a huge part of Iceberg. We have seen with streaming-based workloads as well. It can be a lot. Also, like I said, it significantly reduces the read time merging. That means, at the read time, readers can apply a single bitmap and per data file instead of kind of recompiling all of these different data files. So basically, we are making all of this mutation-heavy and CDC workloads more operational with Iceberg with this deletion vector. Now, moving along, we have this, the way of native support for semi-structured and kind of special data that I was talking about, right? So until now, JSON-based workloads, like for example, like with semi-structured data, what you had to do is you had to flatten it into a dozen of nullable columns, right? So imagine you have a dozen of nullable column. That means your schema is very hard to evolve, right? So there is no native ability to like do things, and you have to really like parse this JSON, row by row, which is extremely hard, can be extremely cumbersome as well, right? So that's where we introduced the variant data type quite recently, and instead of treating this semi-structured data as opaque text, now variant encodes it into a structured form. So that preserves this kind of nested field. So engines can now query, like here's an example, right? I'm not sure if it's visible, but we have defined a variant field here. And now the read query engine can actually access that particular attribute directly without building your own differentiation logic or custom logic around that, right? And there are also other things, like for example, like we recently introduced the concept of geometry and geospatial data. So you can actually represent things like points, shapes, and regions natively within Iceberg. And before that, we used to rely on third-party system to do that. So these are also some newer workloads coming in. That means the industry is also like thinking a little bit more about how these workloads can make sense for Iceberg overall. The next part, I clubbed these two things together. One is the table level encryption, and the other part is the composite partitioning key. Until now, if you have done partition transform specifically with bucket transform, you were only able to use just one single partition key. Like for example, something like bucket of, let's say, 16 of user ID, right? But in practice, analytical queries are more in combination. So for example, you have things like country and city coming together, right? So in this case, previously, we used to end up with suboptimal partitioning, or we encoded multiple fields into a kind of a composite key, which worked okay, but we couldn't take advantage of things like partition pruning and more predicate pushdown capabilities and stuff like that. So with V3, we have this multi transform capability, especially with bucketing transform. So now you can club different partition keys and make sense of that. The other part is the table encryption, and securing data, obviously, it goes without saying that is super important. We used to do that, but more in the storage layer, right? So more file level encryption, more like bucket level encryption and stuff. But now we are getting that natively within the Iceberg table format itself. So all of these things like table key rotation policies can be managed internally within the table itself. All right. That's all about the V1, V2, V3, right? We went from append only to more mutable to more diversified workloads and stuff. Now in the V4, I listed out these 4 proposals in the community that's been going on in discussions. Some are actually landing up in the next couple releases as well. But the most important part to think about these new proposals are, we are now thinking about things from more of a holistic perspective, right? So for example, this is a single file commit proposal. It's a very recent one. The problem with Iceberg is it has a metadata bloat problem, right? We saw that entire stack of the manifest list, the metadata file, the manifest files, and the entire stack of 3, right? Problem is, every time you commit something in Iceberg, it can be a lot of metadata files, right? So in a more technical sense, you don't need to have that. Like, you can simplify that in a way. So the single file commit targets exactly that aspect of thing, right? So basically we are saying we're going to replace this entire manifest list, manifest file thing with like a root manifest that you see it in the purple. And that root manifest will contain the delete manifest and the data manifest, ultimately linking to the data and the delete files, right? So what are the advantages of this? First, obviously, the commits, the performance and the metadata growth should not be directly proportional to the size of the table, right? It should be to the size of the change, the commit that I made, right? Not the size of the entire table, right? So that's a very important part to note, because for streaming and micro batch kind of workloads, you'll be writing at a very faster frequency. And every time you do that, I'm sure you might have ended up with this issue of metadata bloat. But this is the same exact problem we are tackling. And like I said, the whole idea is that now we go from root manifest to data and delete manifest directly from that. So we are simplifying this entire stack of tree and saying now we have a more streamlined way of maintaining the metadata, which was already a kind of a budding problem all through these years. The second part, it also goes well with the first one that I talked about, is basically Iceberg stores all of its manifest list and manifest files as Avro format today, right? That was a reasonable choice, I feel like, because when manifests were relatively small, you were able to typically read entire records, and Avro works out really great for more of append-only kind of things, right? But as tables have grown, manifests now contain hundreds or hundreds of thousands of like statistical column information, right? So in practice, query engines, they only need to read only a few like upper and lower bounds to understand and do more like predicate level pruning, right? So with Avro, there is no way around that, right? And engines must deserialize the record, even if it's just only a handful of fields, right? So that ultimately leads to like CPU uses, memory uses, and planning takes a lot of time, especially for larger table. So now what we're proposing is we basically proposing it to move from Avro to Parquet, and that gives us the columnar advantages as well. So now we can actually think about the same data file benefit that you have with Parquet on the metadata file. So query engines can actually, try to understand what metadata file manifest list makes sense for them based on those statistical information that Parquet already provides, right? So that's another amazing thing. If you combine this with the previous one, that actually gives you a lot of performance benefits already, and we are already testing that across ecosystem and stuff. The third one, this is a smaller one, but again, like it's an important one, I think, how column statistics are represented, right? So currently, if you think about the statistics in the Iceberg, you have the lower bound and the upper bound, and they're basically generic map keys by field ID, right? Now, this is some problem because, imagine if you have a lot of columns in a table, more wider columns, like for machine learning-based workloads, it can be a lot, right? So what we're proposing is that we are putting everything, we're giving every stats like a map form, and every column will have their own key, and they will have their own statistical information internally within that. So it's a more tight representation, more structured representation, and engines can read individual statistical file rather than reading their entire kind of column set in the memory and trying to make a sense out of that. And this final proposal it's a long-standing problem. This is where we're talking about moving from absolute-based URIs to relative-based URIs. Today, Iceberg stores all of this information, like with metadata file, manifest list, all of this, as absolute URIs. That means if you want to move a table, you have to rewrite all of these things and think about all of this absolute URIs, right? So for use cases like disaster recovery and replication or multi-region deployment, this is a pain, really a cumbersome pain. So this is where you're kind of like, you're not just copying the data, but you're rewriting the entire stack of things. So Spec V4 proposes supporting relative path. We still will have the absolute path, but there will be the notion of relative path. So that way, it looks like a simple copy. I have just simplified the diagram in a way. It'll not be that simple, but in a way, it's a more simpler operation than you would need to do with more like absolute URIs. All right, final piece before I end the talk. One of the most important thing for Iceberg grew the way it did because of the community. Every bubble you see here is different companies like contributing to Iceberg, making sure the community grows and remains more vibrant, more vendor agnostic, more vendor neutral, so that one particular vendor doesn't have a control on Iceberg, right? So, you have different companies like Tencent, Cloudera, Netflix, Dremio, all of these different companies are making sure the contributions are more varied and verified in the community as proposals. That's how we saw all these proposals being made, right? So we are still discussing on the proposals. If everyone agrees, we go ahead with that particular thing. All right, so this is my shake in a way. We introduced Cloudera community. You're open to like join that up with the Slack link. I personally write a lot. I'm going to publish a lot of the things in this community. There are a lot of discussions going to happen in general. We're trying to bring in certifications for like lake houses, how we can make sure our community remains more active, more vibrant. If you're interested in contributing to Iceberg and the community of different things around that, that could be a good way to ask questions as well and seek any help from the committers, from people like who are in the community and building towards that. So that's my time. Thank you so much. I'm open to any questions that you might have. Sorry, Samriddhi, I took a little bit of time there.
So you mentioned about that manifest list, right? It is going to be replaced with root manifest, right? And we have one-to-one mapping between snapshots and manifest list, right? So what is the main difference between root manifest and manifest list?
So the snapshot reference today is primarily in the metadata.json file, is it, right?
Yeah.
So that's where you have the current snapshot plus all the existing snapshot because of you need to do time travel and rollbacks and stuff, right? Manifest list today maintains, it's kind of serves as an index, right, for those manifest files, right? So we are trying to get a step out of that like process because technically a lot of the things can be done directly from the manifest files itself, right? Because our goal is to basically like prune out all of this file that are relevant to the query, right? So I think the notion of that is basically we are not replacing the idea of snapshot. That still will contain that reference. The root manifest will still have that reference. I think we're cutting a hop in there and bringing in like more streamlined approach towards like, okay, I don't need to really think about writing it as a manifest list, another Avro file and the Perky file, whereas I can just club it together as like a root manifest and bring it all together into one format. I think that's the notion overall. And by the way, this is still a discussion in the community. So I think I see the similar questions coming in as well. But I think that's the overall idea in general.
Okay.
Yeah. Sorry?
Will that eliminate the time travel feature then?
No, absolutely not. I mean, like, this is something super critical, of course. Like, so like I said, like I do think that metadata JSON like is the core source of truth for snapshot, historical or current, right? That still remains untouched. The reason people were thinking about proposing this was, like I said, I think we do not need to go to that extra step of like writing it as an index just to get to that manifest file itself, right? So the way to think about indexes, right? Indexes are hard to manage, right? Even in a simple database system as well. So I think we are trying to get rid of that particular indexing system in a way, like manifest list, for example. And we're still going to have that time travel abilities with snapshot in the metadata file.
Thank you so much, Dipankar. In interest of time, we will move to next because she has to catch flight as well. She will take just 2 minutes. She's from our talent acquisition team.
Awesome.
Thank you so much, Dipankar. He is here. I really apologize.
chat,
You have some more questions but could not address. Feel free to, bother him.
Right.
Thanks, Dipankar. So I request Shreya to come and take 2-3 minutes to talk over it.
Good afternoon, everyone. I am Shreya from the talent acquisition team, and it is great to see this turnout and great to see the enthusiasm that we have out here. As Samriddhi said, I won't take a lot of time. For us, I'll just give you a little bit of sneak peek into what Cloudera Life actually is. So open source is not just a technology choice for Cloudera. It is basically the foundation of who we are. I'm not here to talk about Cloudera or technology or Cloudera is into the open source community or how we are a pioneer in the enterprise data platform side, and helping companies manage, analyze, and activate their data. I'm just here to give you a little bit of sneak peek into the culture that we have at Cloudera, and we call it as Cloudera Life. So we believe that sustainable innovation is only possible when we trust, empower, and support our people. We follow the principle of people first. And here is just a small sneak peek into the kind of perks and benefits we provide at Cloudera. First thing going ahead is that we have global unplugged days. Every 3 to 4 weeks, we ensure that our employees get a little bit of a break from the work routine. We have either a long weekend or maybe like 3 days off, Friday, Saturday, Sunday, or maybe a Saturday, Sunday, Monday. Sometimes if we get lucky, we also have a Friday, Saturday, Sunday, Monday off. And 2 times in a year, we have a full week off that we give to our employees, giving them the opportunity to regenerate, recharge, and then get back to work. We have some comprehensive work culture. I think during the onset of COVID, we all went into a remote working environment, and then with COVID settling, we came back to a hybrid model of return to work, sometimes 4 to 5 days. Also, however, Cloudera still following one of the best industry practices, and I would actually say leading it in that front. We have all sorts of working options available, be it work from office, a hybrid model, and even opportunities given for 100% remote working option available. We follow Zoom-free Friday Mondays, ensuring that you ease into the weekend in the right way. And we have some comprehensive onboarding programs, making sure that whenever somebody joins us, it's never an overwhelming experience. You are given the opportunity to ease into your team, your work, and into the culture in a very smooth way. Employee assistant program, of course, all of us have things going on in our life, and we want to make sure with our people first option to be there, wherein you have opportunities to reach out, ask for help. We have webinars, counseling sessions that are always available to our employees whenever they need it. Career progression is something that we take extremely seriously at Cloudera, with not just internal movements, but proper coaching, career pathing, given equal importance out there. We have self-learning course opportunities via Udemy, which are always given a priority to ensure that self-learning, upskilling matters to employees as much as it does to us. And of course, one of the major perks that we have out here at Cloudera is encouraging our employees to take up courses, education courses, and offering a certain level of reimbursement to it. For us, upskilling is more important as an organization for us than it is for employees as well, because we believe that when you grow, the organization would grow as well. Of course, there are social bonding activities that we have. We keep on having sports tournament, festival celebrations together, and fun meetups, something like this. And in fact, last week only we had a full wellness day organized, encouraging people to, sort of also focus on their health while they're also focusing on their careers that are there. Samriddhi, can you? Samriddhi, yeah, sorry. So for us, people first is something that we, sort of value the most. And here there are 2 QR codes that I would like you to scan. We encourage open source community folks to join us and look at the opportunities which are currently open. I would also request you to follow our LinkedIn page for future possible openings that are there. My name is Shreya Vishishta. You can reach out to me or anybody in our talent acquisition team to connect and discuss about joining Cloudera as a part of your future possibilities that are out there. So please feel free to reach out, and I'm just again very glad to see this turnout. So thank you so much, and I'd now like to hand over the mic to Samriddhi for taking it forward. Thank you so much, and if there's anything, happy to connect on LinkedIn to take our conversations of working together in the future as a possibility. Thank you, everyone. Thank you.
Hey guys, thank you so much for turning in. I'm Harsha from Oleg team, co-host of this event. And next up, we would like to invite Diptiman Raichaudhuri from Confluent. He works as a staff data advocate, and so glad to be here. Thank you.
My name is Diptiman. Good afternoon, and it's fantastic to see so much of you guys participating on a Saturday afternoon. So first, a big round of applause for Bengaluru. Nowhere else this happens. Nowhere else. Thank you very much. So my name is Diptiman. I'm a developer advocate with a company called Confluent. And Confluent was founded by 3 engineers who invented Apache Kafka. So I mostly work on streaming data storage and stream processing. But very lately, for about a year and a half, we have been working very closely and deeply for developers and users to ensure that our Kafka data, which we store, is available to query as Iceberg tables as well. So that's when I got the opportunity to work with Iceberg a little closely. And in my previous life at Google Cloud, I was a data platform specialist. We have worked a lot on Iceberg. Similarly, I was at AWS as a principal architect. So there was also, and it's good to see Iceberg taking shape, the shape it is where it is now. But today I'm going to talk about something a little different, not on Iceberg semantics per se, but how do you process Iceberg tables? And this talk was inspired by my visit at Small Data San Francisco conference, which is hosted by DuckDB, Mother Duck. And regardless of whether you have big data or whether your data size which you query is, let's say, not even hundreds of GBs, you should be able to work with PyIceberg. And that's what my talk is all about today, where you can create simple data engineering pipelines without a cluster using PyIceberg and PyArrow. So quick warning, not a single LLM was exploited or harmed to make my presentation. I do have a demo. It fails at times, but it mostly works. So it's 100% human-generated content, no AI. And this is broadly what I'm going to talk about. 30 minutes I have. I'll finish it within that. So let's start quickly with why iceberg. Dipankar has already talked about most of these points, but just a quick recap. So we start with this diagram, which I took from the book Iceberg, the Definitive Guide from O'Reilly. And believe me, when I talk about data platforms, it applies not only to lakehouses or data warehouses, it applies to databases as well. So most of these layers, as you see, which are called composable architecture layers in data platform parlance, it starts with storage, which lets you a place where you could store your files, right? And then, of course, second comes the file format itself. It becomes easier for running queries if the file format supports columnar storage, because columnar storage gives you the opportunity to query huge data sets as well. And then, of course, the main topic of today, table formats or open table formats, OTFs as we call it, which enables you to run data manipulation languages, inserts and upserts and deletes, etc., and moves your data lakehouse or a data warehouse from a read-only system data platform to a system where you would be able to do data manipulation language as well. And then you have the top three: storage engine, compute engine, and catalog. Compute engine is predominantly the component which lets you query your data. Catalog gives you an option to have all this metadata of your tables, a data dictionary. 15, 20 years ago, we used to call it, some still call it data dictionary. Now, a more common term is catalog or metadata, etc. And then, of course, you have storage engine, which lets you create lets you store your indexes in a way you would want, and which is similar to things like, let's say, MyISAM or InnoDB, or if you come from a PG-SQL background, you would realize OrioleDB is one of the, and then Neon is also, they have their own storage engine, etc. Citrus Columnar is a storage engine which is based on PG-SQL storage, but then they have created their own extension, right? Now, a lakehouse is built using these layers, and what makes a lakehouse stand apart in the data platform world are these composable layers. You can actually plug and play most of this. So it remains, you could make it completely open and ensure that there is no lock-in with any vendor whatsoever, or else you could also work with vendor-defined stores as well. So a lakehouse lets you use this, and you could bring in your own stuff. So for storage, it could be even your SSDs or HDDs. It could be your S3s and ADLS and GCSs of the world. Your file format could be mostly columnar splittable. If you have columnar file formats which is splittable, like Parquet, Lance, Vortex, etc. Avro is also possible, although Avro is not a columnar file format, by the way. So keep that distinction very clearly in mind. And then you have table formats, right? So normally we call about 3 table formats, and 3 are open source, all 3. Iceberg, Hudi, and Delta. But today we are focusing on Iceberg, and especially in my talk, it's only PyIceberg. So I've kept only Iceberg. And then you could bring your own query engine. So DuckDB is one of my favorites nowadays. For the last 1.5 years, I've been working very, very closely with DuckDB. Or else it could be Spark, it could be Trino, it could be Flink, all open source. And you could have your catalogs as well, both open source as closed source. So you could have Apache Nessie, you could have Apache Polaris, or you could have Databricks Unity, you could have your AWS Glue, etc. So again, you get the point, right? So the design motive is to have something which is composable using open source as well as closed source layers. So the goal of that middle part, open table format OTF, is to have DML capabilities in your file storage. If you come from those olden Hive Metastore days, we used to treat it as read-only alone. And batch operations would keep your data, you would refresh your Hive Metastore, and then those dreadful years of my life, which I call the death of my youth, I have spent writing MapReduce code and shufflers and combiners in Java MapReduce framework. Never liked it a bit. And then, of course, around 2015, I changed my religion to Python. And now every single day I pray to my green snake, and I'm so happy. And that's what has sort of nudged me towards this talk. And of course, it provides you an ACID guarantee. So you get Iceberg, which would support all the traditional database, data warehouse concepts like atomicity and isolation. And long story short, your data remains consistent and durable even after all these operations are done. And it also supports schema evolution. Schema evolution is a reality you can't deny, but your data, your open table format should be good enough to understand and react to that. So thus comes Apache Iceberg. It's an open table format for analytical data sets. And of course, it brings the simplicity of SQL tables for querying. And it's a famous diagram. I don't want to spend a lot of time. Deepankar has already spent a good amount of time on this. So you end up having a catalog which points to a metadata file, which is the primary pointer. And then for time travel, you sort of move that pointer to other snapshots so that you could go ahead and query on your previous data. The manifest list and the manifest files does their job. So it would give you your min-max statistics of the underlying data so that you could push the predicates down a little bit and make sure that your query doesn't scan a lot of data and remains constrained and zoomed in and zoned in on very specific data files. The data storage is mostly Parquet, but again, Lance, Vortex, these are good upcoming formats. So why Iceberg? It's the interoperability. So Iceberg at its core is nothing beyond the spec. It's a very, very well-written spec, which is now evolving. Of course, V3 is the current version, V4 would come in. And interoperability is what the spec preaches. And it talks about bringing your own query engine, bringing your own catalog engine, have your own file format, have your own storage engine, etc. But build your data platform in a composable way. So that has been the philosophy for Iceberg, right? Now, let's understand why PyIceberg then. We understand what Iceberg is, right? So again, doing a quick recap, it's a set of specifications, which is very well written again. And it is released as a reference implementation as a set of jar files. So if you go to iceberg.apache.org and you click on version 1.10, you would see a set of jar files, right? Which would let you build your own OTF layer on top of Parquet format, etc., etc. So this is a vision, right? The vision is I'll have my Iceberg open table format on top of my data, bringing my own query engine. But then what is the reality? The reality is still I have those jar files, which are the reference implementation, and I bring on my JVM clusters, which could be huge, mostly huge. And then I do query these things, right? So the problem is Python data engineers like me, we lack the ability to natively integrate with PyIceberg. PyIceberg doesn't enforce that you need to query with SQL. Never ever in the spec it talks about SQL as your own query engine. So why so serious? Right? So this is the primary motive behind having something as PyIceberg at all in the first place, right? And this is my own pet peeve, right? I'm a Python data. I don't even care about anything else. You just give me a notebook or a PyCharm or a VS Code. I'll do an UV add. I don't need a Docker compose up on 1,000 different things and my port gets blocked and I need to call a network admin to unblock. And I don't need to go through all this. And of course, Py4j is a nightmare which has kept many data engineers and administrators awake. God be with them. But PyIceberg doesn't use Py4j whatsoever. So I want a system where I want to do pip install and go ahead, do an UV add. I want integration with PyArrow because I want my transfer to downstream systems absolutely super duper fast. I want my schema data types to be compatible with PyArrow because I want to use PyArrow. I want to use PyArrow batch record batch readers, so that my queries are super fast. And I want a Pythonic fluent SDK. God, for the love of God, I don't want to use SQL. That's where we enter. And we call all data engineers to be united on PyIceberg. And what PyIceberg is a Python implementation of the spec, of the Iceberg spec. Currently it's version 0.9. If I'm not wrong, I didn't check for some time, but we are moving fast towards the 1.0 release, and you should hook up at Slack and on the GitHub, right? So what does it do? It lets you use Python core, native Python functionality. And when I say native Python, I mean it doesn't use anything else underneath, like a PyO3 Rust and stuff like that, right? So it's a native Python for loading catalogs. It supports all catalogs, REST catalog, SQL catalog, Hive and Glue and all these things. And it would let you run all those discovery operations, listing namespaces, dropping namespaces, listing tables, etc. And it supports most of the file systems. You can go back today and do it on your laptop with an SSD. You could build a small lakehouse with PyIceberg, insert, let's say, 50,000 rows, start with some upserts and deletes and see how it works. And it does support all the CRUD operations. The schema is interoperable with PyArrow. So you have the Iceberg's catalog schema data types mapped directly with PyArrow data types, blazing fast exchanges. And then you could define your partition using a partition spec, which is part of the specification, Iceberg specification. And you could do it either a timestamp bound, or if you come from an HMS Hive Metastored days, you could actually do a year/month/day kind of a setup as well. For read, PyIceberg uses PyArrow record batch reader. So you could do a table.scan and you can put your predicates there, and it would let your scan area gets reduced. And then you could push down those predicates again based on the metadata that PyIceberg would do automatically. You can convert the result to an arrow data set, and you could pass it on to whoever wants it. So it's blazing fast. There are one limitation today. On the read side, it doesn't have the capability to read equality deletes yet, which is being worked upon. So it still uses only positional deletes for the read path. For write path, so it supports append, upsert, overwrite, insert all together, but only on copy on write, COW mode. It doesn't support merge on read today. And if merge on read changes, the last I saw was the PyIceberg spec is also contemplating that merge on read would be handled a little bit differently. It supports partition writing as well. So from read and write, it also has a nifty CLI tool which you can which you can install, and you can quickly query the metadata, listing tables, listing namespaces as well. So namespace in an Iceberg parlance, Iceberg jargon is nothing but like a schema where you put all your tables together. And the beauty is you can have JSON output, and you can get the JSON output, pipe it with a JQ, and you can figure out a lot of things yourself. For the admin kind of tooling, you have inspection API, which lets you peek inside your partitions, your entries, your metadata, your manifest files, your manifest lists, your history, etc., etc. And it gives you back this result set, which you can work. If you're working on MCP, that's like a great tool because you can MCPify the whole thing. And you can convert these result set into pandas or polars or daft. They all work together. Especially DuckDB as well could be used as a query engine. So the goal is to start simple and stay simple. So if you look at it, you just need a .pyiceberg.yaml file where you create a catalog name. And for this one, I've used an SQLite catalog. And then you just define a data warehouse. So I've defined, let's say, DW1. And then what you could do is you could just insert this data using a PyArrow batch. So you could just push your lists within PyArrow, and then PyArrow would insert it or overwrite it or append it. And you can run upsert operations as well. So nobody stops you from doing that. So key takeaways is simple and effective. So it gives you the native Python experience, and it integrates very well with Arrow, Pandas, DuckDB, Daft, Polars, Ray. In fact, Daft is doing very, very well nowadays, is what I've heard. And you could try it out on your local notebook, local VS Code or PyCharm, or you could have your notebook. But before I end, I wanted to talk about a little anti-patterns, couple of anti-patterns, which you should clearly understand that Iceberg might not be solution to all your data management platform or data platform issues from both a design and the architecture and an execution perspective. So you keep these things in mind, right? So this is that famous small data SF image, which has come from Jordan Tigani's talk. And on the right-hand side, we have this Redshift data hunt. It's called a Redshift Red Data Hunt, which was started by two engineers at AWS they were curious to understand, to figure out how much data actual average queries would run on. And the result was absolutely mind-boggling. The result was 99% of their queries were against smaller tables, which was less than 10 GB or 50 GBs of data. It was a resounding number which surprised a lot of people. So please keep that in mind. Columnar systems, lake houses, etc., it is created for a purpose. So you got to have very clear-cut goals in terms of achieving data platform results. So you should be mindful about that. And the metadata maze is still something you'll have to live with today. So an innocuous looking query like update orders, set point of sale status equal to something where point of sale ID equal to something would actually go through that whole list today. It will go through this list. It would generate metadata files. But then again, compaction is something which you could do time to time. In fact, the way our engineering team has worked on compaction is very, very closely monitored, and we have both time as well as size-based triggers, which initiates compaction, etc. But then this is something we call it a small price to pay for remaining completely open and not locked in with any vendor. You can move around your stuff on cloud or on-premise, on containers, on everywhere. And so Dipankar showed you one of the V4 things, right? Regarding the metadata and the root manifest, etc. This actually I captured when I went to the Small Data San Francisco conference. So Mother Duck has their own sort of proprietary way, of course, but then own sort of proprietary way of making sure that catalog management is something which is not handled in a file-to-file basis. So what they propose is to have a database to have this entire metadata operations so that it is closed and it is bounded, etc. A good take maybe. Time will tell whether it takes off or not. So always remember there is a trade-off. Either you use Iceberg in its fullest form to ensure that you get all the complex features for running your own enterprise business use cases for your own company or your customers, versus you could have an ease of use and you could decide that whether I want to go the whole 9 yards or whether I can make a lakehouse which is easy to handle and small because my complexity is not that much. Believe me, that architectural decision would be needed for 90% of the cases. I've been doing this for almost 15, 20 years now, and I've seen it so many times. How to contribute? So this is the Slack channel. It's fairly active. And this is the GitHub for Iceberg Python. If you have anything, you could raise an issue and somebody would respond on a best effort basis. This is a blog which I've written to have an MCP server created using FastMCP for a PyIceberg. Very simple. It's a point of sale device data where I've created 4 or 5 tools using FastMCP. And you can call those using agents like LangGraph or AWS Strands or Autogen, or you could run it on an STDIO and do it with Cloud Desktop as well. So that's it. If you have any questions, do I have like any minutes left? Yeah, okay, perfect. So if you have any questions, happy to take it.
If you can go back to the slide where you talked about the Redshift stat, right? Okay, so what were the use cases here? I mean, this is an eye-opener for me.
Yeah. So this has actually come out in GitHub. They have published all their report. It's mostly on retail, manufacturing, and healthcare domains. And what they have done is they have tried to capture most of their Redshift clusters, and they have analyzed the average query size, average data size on which most of their queries run. And this is their finding. It's absolutely surprising and shocking.
Definitely, this is.
And this is called the report. It's called the TPC is not the. So what they so that their motive is simple, that you can't use TPCH and TPC-DS only to test your performance benchmark for your data platform. Those are good, but then moving from scale factor 1 to 10 to 100 to 1,000 to 10,000, it will give you some idea, of course. But then your TPC is not going to. So what they have actually found is queries are more than 50% diverse in nature than what a TPCH or a TPC-DS dataset would actually define. So you get it, right? If you're building your own data platform for your company or for your customer, and the customer says, "Boss, are you performance tested?" Yeah, absolutely. We have tested for scale factor 1,000. And my query runs on 691 million records. You have to take it with a pinch of salt, really. I mean, whether it actually defines the complexity your project would have or not is a bigger question. And this analysis actually talks in depth about that, this paper, two engineers from Redshift. But this is more surprising, that 99% of the queries run on less than 10 GB of data, actually.
Exactly. I mean, so if you're talking about retail space, right, and let's say if you're talking about hyper-personalization, at least in my 15 years of what I've seen, the data volumes run into petabytes. If you're doing.
But then there would be, I can tell you for sure, I have seen so many retail organizations with data platforms of no more than GBs in data size as well. So it's just the need of the hour, right? If you have petabytes, you should have something like that, like a full-blown Iceberg thing. If you don't do it. You just install you just get a VM on one of the hyperscalers and run DuckDB or PyIceberg. You don't need anything beyond that. So my point is, it depends. The answer is always it depends on the kind of workload that you're running into. Your workload should define your architecture, not your TPCH or TPC-DS dataset is what it's so easy nowadays to have all these scale factors and run these TPC-DS datasets, but it's not the end of the road is what I strongly believe.
Sounds good. Yeah. Thanks.
Thank you for your question.
I just have one question. As a part of a banking organization, I'm working for a bank as a data engineer. I just wanted to ask more on the PyIceberg that you have been showing. We basically did not have much idea about the PyIceberg or basically about its existence. So what we started doing is we initialized Iceberg within the Spark contexts, and that's how we started using it.
Yeah.
So are you saying that if we switch to PyIceberg, by the way, PyIceberg, I mean, this is actually a Python tool.
It doesn't use, so Spark uses Py4j, right? You know?
Right.
So it doesn't use Py4j. It's a Python implementation of the Iceberg spec. There is no JVM runtime which runs it.
Okay.
So for the data exchange, it uses Arrow. It uses PyArrow. So that's the difference. Now, again, whether you should switch or not, that's your decision.
Okay.
You need to understand and check and figure out whether it works or not. But what I'm trying to say is with PyIceberg, what happens is your query runs not on a cluster, right? So you could actually have a single VM and you could just have a notebook and run it, right?
Yep.
So which is a significant difference than running it on a Flink or a Spark cluster. which are fundamentally differently built, right? These are built in with JVM for specific things in mind. You have executors which are completely blind, and you have some managers. I mean, good old days of Yarn kind of resource management, right? So these have automated resource management, auto scaling involved, and you can actually run into, let's say, thousands of spot instances if you're on AWS, and you can make your query processing a lot fast.
Okay.
But my whole point is, whether you need it or not, maybe you should ask yourself once,
Okay.
and then you go ahead with it. There might not be a need as well. And if you don't need a cluster with all the bells and whistles and fancies,
Okay.
PyIceberg should work absolutely fine for you.
Okay. Yeah. So with and I'm going to ask a very basic question. So whatever I have been able to do, say any mathematical operations, whatever data transformation operations, using initiating this Iceberg within the Spark context, I will be able to do the same thing in PyIceberg also.
As long as it's part of the Iceberg spec. So mathematical operations, if these are, so I consider aggregations as relational like relational operations. Now you call it a mathematical or not, I don't know, but you won't be able to run like a NumPy, let's say, tensor operation right using PyIceberg, right? For that, you might need your VM compute, and I strongly suggest you use CUDA or MPS kind of systems to have your mathematical operations. But as long as it is within the purview of your Iceberg spec, aggregations, transformations, upserts, deletes, converting to pandas, converting into polars, all those things would work absolutely fine, because these are very, very well connected using PyArrow. So what happens is the transformation that happens from your PyIceberg result set to pandas takes place using PyArrow. You don't even feel it because it's blazing fast. It happens in memory. But if you're using something like a Spark ML library for a very specific mathematical operation, let's say tensors, that you won't be able to get in PyIceberg. Of course, no.
Okay.
Yeah.
Okay. I do have more questions, but I'll just
we can chat
later.
afterwards. Yeah.
Thank you.
No questions? Oh, you still, my goodness. I just thought that there wouldn't be.
If you
any more
don't mind,
questions.
can you please connect with him?
We'll catch up later.
Yes. Thank you so much.
Okay. Thank you very much.
Thank you so much, Deeptiman, for the amazing talk. With that, I request our next presenter, Ankit and Badal from Oleg by DataZip to present the next talk, please. Thank you.
Hello. Hey, hi everyone. Myself Ankit, and I'm lead engineer at Oleg. And yeah, so as my fellow speakers already talked about Iceberg and a lot about like JVM based Spark and also the V2 and V3 versions. And if you have attended the previous Iceberg Apache meetup in the Bangalore itself, our CTO itself told about like what are the challenges in the evolution of Iceberg. But today we are going to discuss about the writing part of the Iceberg, where we are basically telling about the data ingestion using our tool, or maybe in Apache Arrow, whichever you want to use. So nevertheless, let's get started about it. So first of all, if you are moving your petabyte scale of data or maybe terabyte scale of data, you will require the concurrent writers, right? So for that, you have the major problems that I'm going to discuss. Those are those like conflict between the writers. Let's say you are writing different partitions, and in different partition, what will happen? Let's say one partition is writing in the region and the other partition is writing in the address. So you can have the both of them can have the same value, right? So that can be a Bangalore, and that those can end up writing in the same Parquet file, which is again a conflict. The other thing is the metadata bloating. Let's say you are, if you have heard about the Dipankar's presentation, they have already mentioned that every write is going to create a snapshot or metadata here. So there is a chances that, let's say you are syncing your data every minute. So think of it, in one day you are going to have the 1440 syncs, and those much of your meta snapshot will be there. So that's the kind of problem. Thank you. So the third problem is the schema mismatch. So let's say you are writing through the different writers. What will happen is, let's say one writer has evolved the schema. What will happen to the next writer, and how they will connect with the global schema, or like how they will maintain their schema with the iceberg table. So that's again the problem. The fourth problem is the manifest explosion. So if you have read the previous conversations about the PyIceberg, so there is this manifest thing. The manifest thing is a homogeneous file where you only can have the data files, or only can have the delete file, or maybe the cluster of that. So every time if you are writing the MOR, you always going to have two manifest files, because one for the delete and one for the data. And if you are writing COW, then only going to have, like I'm going to discuss about this in the next slide, but only going to have one manifest file for that particular thing. So yeah, you can see in the diagram that I have already shown how manifest structure look like the OZ diagram is already been shown here. So I'm not showing that. Here you can see like the manifests are there and how data file are being referenced. So manifest is nothing but just you can say metadata information about the parquet or the columns. It also store your metrics of the columns, like what is the max bound and what is the lower bound. So all this information is there, and also manifest can reference to the previous snapshots. These manifest file can also reference to the previous snapshots. So that's again a problem. Like if you're not like you're maintaining the versioning and you are not expiring the snapshot, that's again going to be a problem. So these are the problems that concurrent writes going to have whenever you are going to move your petabyte scale of data. Before jumping to the solution, I would like to tell you first about what are the basic, or what is the basic we should follow. So as in the previous slide, or I have also mentioned this, every write is going to create a snapshot. So we can't run away from this. So this is the base thing here. Every write is going to create a snapshot. The second thing here is the optimistic locking. What happens also, like as Dipankar mentioned, that V2 is the one for backfill and CDC. Like if you are having the use case, V2 is the stable one right now. So this optimistic locking is still there. Like what happens in that is, let's say you have you started writing metadata from V0, and right now some other query engine written the V1, and then again comes to you are writing it again. Like you have the reference of V0, but right now metadata location in the catalog itself is changed. So what will happen is there will be a conflict. So that's how the CA strategy comes into the picture. Why CA strategy? Why it's optimistic strategy is there? Because Iceberg wants to be read efficient. It don't want to lock your reads when you are writing in it. So the third one is the let's discuss about like three writing strategy as I mentioned, but there are four. So first one is the append only. In append only mode, let's say you have the backfill. You have to do historical load of your petabyte of data. You don't need to. You can take a snapshot. You don't need to take care of upsert. You don't need to take care of change stream. So what you can do is you can directly append the data files there, and you don't have to add any delete file there. So and also in append there is no conflict checks are required. The second one is the overwrite. What is overwrite is, so as I mentioned in the previous, like snapshot you can take and you can load the data, but there are updates also coming and change stream data is also coming. So how you will manage that? So to manage that, you have to write the delete files, or you can do some sort of compaction or on the fly upsert in the iceberg table. So you can use the COW and copy on write, where you are reading the whole table, whole file, and then merging the change stream data inside it. The third is MOR. You can also use for this incremental or the CDC change stream data MOR. This is merge on read, where you have two things. One is positional date, one is your equality dates. So if I define them, positional dates is nothing but just like a book. You are searching for a book in the library where you have an aisles and also the bookshelves. So you have the location where you have to check the book. So that's the positional dates also work. So you have that particular location which data need to be deleted. But in equality, you don't have that. You have only the this identifier field which need to be removed from the data, which is going to be only removed while reading. So read will be slow in the equality dates. But in positional dates, your read will be fast, but write will be slow. So these things are there, and the last one is the conflict checks. So let's say, as I mentioned, positional dates is having the reference of the data file. So what will happen if the data file don't exist there? That data file which you are referencing in the delete file. So those kind of conflict checks are also required while writing to the iceberg. So these are the basic I have told about. But now, what will be the solution for that? Like how we can solve the problem? So we have already. If you have any questions. Okay, let me move forward. So here we are contributing, like we have developed a engine which is Oleg, which is ingesting data from databases, which is MongoDB, which can be MongoDB, your Postgres, your MySQL as well Oracle. Also, we are supporting now S3 and Kafka as well. Like S3 is in the process. So you can ingest data directly in Iceberg format from here, and it's very fast. And I'm going to discuss how we are solving those problems that I mentioned in the first slide. Yes, so let's start it. So here, first of all, you have the DB, and DB has the that particular petabyte of data. What will happen? We make sure that we put out the chunks. We create those chunks in big size so that we put inside the file in a bigger, like a big file. And also, only one snapshot will be created for one particular chunk, as well as there will be only one metadata file will be there. So every time, if you are going to, like, as I'm mentioning here, every time you are going to write MOR, there will be minimum 6 files will be generated. And every time you are writing COW, there will be minimum 4 files need to be generated. So we can't run away from that. So that's the fact. Here, we are creating the chunks, and then we are writing them directly and only creating one single metadata or file. As well as we have the atomic locking, where what we are doing is, where, let's say, as I mentioned about the schema evolution, right? So schema evolution writer, how they will get to know about that. So what we do is we have the writer threads, as you can see in the picture as well. So we have the writer threads, which is honing out there are one schema, and what will happen is, let's say there is some change happens, then the global schema is there, which is being maintained, and being using the hashing is being checked if there is any change, and according to that we roll the schema in the Iceberg table. Other than that, also, like as I mentioned about manifest bloat, right? Manifest explosion. So in manifest explosion, what happens is, to manifest, we only write at a metadata, like at a particular snapshot when we write. Why? Because we have all the data files collected and all the data file collected, and we just push them in one single manifest, two different manifests, because these are homogeneous files. Yes, so that's how our solution work. Yes, and talking about the benchmarks, like after implementing this solution, we have also calculated our benchmarks with regarding the popular ETL tools. So it's 3020K, which is again 7x faster than the other tools in the market. I have not mentioned the names. You can check out on the website. I have given the link as well. Yeah. If you have any questions regarding it, I'm happy to take. Like, anyone want to know how Positional works, how metadata explosion happens, anything? Okay. So on to Badal now, about the Arrow thing, like how we are emerging Arrow in Oleg. Yeah.
Thank you so much, Ankit. Very good afternoon, everyone. As Ankit mentioned to you about the multiple writer conflicts we have while ingesting our data into Apache Iceberg, we as a team kept on innovating, kept on developing new ideas how we can improve our writing strategy while writing into Apache Iceberg. So the very first thing which came into our mind was Parquet is already a columnar format. So while ingesting the data, why not, if we have our data predefined in a columnar format and then just write into it? That would increase our ingestion speed by quite a long time. And nevertheless, we found out a pretty good solution for our writer architecture, which is none other than Apache Arrow. As our previous speakers have mentioned the benefits of Arrow, you might be knowing, but still I will cover the basics. Apache Arrow is a columnar format, and it gives you zero copy reads. What I mean by zero copy reads is that if you have the data in memory already, instead of copying the data in memory, you can just pass on the memory address and just move it forward. That's something how zero copy actually works. Again, Apache Arrow also gives you the feasibility to not always serialize and deserialize your data. So it eliminates a lot of serialization and deserialization, which I will discuss was one of the primary caveats in our previous writing strategy. None other than that, Apache Arrow also comes up with an inbuilt Parquet integration. So once we have been using the Arrow library, we don't have to depend on another library to write the Parquet. That was one of the major primary benefits. And also cannot ignore the system benefits of how Arrow is cache friendly and also uses a lot of SIMD operations to compute fast. So in the slide I've mentioned, we have two writing strategies, our previous writing strategy and our new writing strategy. So we are an open source Golang project, and Apache Iceberg in its most stable version is a Java project. So what we have to do is that once we take the data from source and we have in Go records, we have to write Parquet from it. So we have to do multiple times of serialization and deserialization over gRPC network calls until we reach Apache Iceberg and write those data into Parquet files. So as in the innovation team, we try to think a lot, do a lot of brainstorming how to improve this. So one of the primary things we came up with, why not as an ETL tool, we write directly into Parquets and let Iceberg build the metadata layer on the top of it. That was one of the primary hypotheses we had. So that was the primary reason we used Apache Arrow for, to write our data as well as delete files. If you know, both of them use the file format Parquet, and then using the Iceberg API, create the metadata layer on the top of it. So this is a very basic architecture of how we use Apache Arrow as an architecture. So as an ETL tool, we support 5 of the primary sources, which is Postgres, MongoDB, MySQL, Kafka, and Oracle. And we are also upcoming with S3 and Snowflake as one of the sources. And what we do is that, as Ankit mentioned you about, we use chunking strategies. So we build a lot of chunks, and because we distribute the source data into multiple smaller part of chunks, we can use parallelism a lot, which increases our speed of ingestion into Apache Iceberg. And that is one of the primary reasons which we got the benchmarks as well, which Ankit just showed you. So what we do here is that once we have the data in multiple threads, we convert them into Arrow records, and using a fan-out strategy, we write into Apache Iceberg. So in a regular use case, most of our times the tables are partitioned. So using fan-out technique, what you do is that you distribute the data across multiple partitions. And then you use the concept of rolling writer to write the data files and the delete files into the desired location. So what a rolling writer concept is, you pass it a target file size, and once your writer reaches the target file size, it closes the open Parquet file and flushes it into the required destination. That's the whole concept of a rolling data writer. And as Ankit mentioned we currently support equality delete writes. So why equality deletes? Because it's very fast as an ingestion tool to write. Because in case of a positional delete, you need to mention the exact file location where your delete file is supposed to materialize. So that's why we use equality deletes, where you just pass on the column value which you want to delete, and that's it. And that's, you can just simply ingest into the desired location. So that would be a very simple architecture of the Arrow writer. Moving forward, this is a slide where I would say why even Apache Arrow is so fast. So the very basic principles, as I told you earlier as well, it gives you the leverage of having zero copy, SIMD operations, and having efficient compression. So right now we support ZSTD compression with a compression level of 3, and Arrow as a format where it highly uses the system programming features of SIMD features. It helps us generate the Parquet files 1.5 to 2x faster than what we were previously doing with our gRPC calls. That was the major benefit we got from Arrow, and that was something which also increased our performance as well. Not only towards the RPS, where we say rows per second, but also towards the memory utilization basis. And if you can see, this is Iceberg Go. So we as a team in Oleg have been actively contributing to the Iceberg Go project. And Iceberg Go project as well uses Apache Arrow heavily a lot to write and read. So that is something in this slide. So as the speakers before me and as Ankit also mentioned how Iceberg primarily works, so I won't go too deep into the basics of how Iceberg works. But I would say that while developing this writer, and since we are using equality deletes, we had to take a lot of things into our consideration, because since we are using multiple threads also, so we have to maintain the sequence number of how we are passing the equality deletes. Because if you mess up with the sequence number in Iceberg, your equality deletes won't work properly. That is something you have to take a primary take care in your or test case in your head. Second of all, what happens if your equality delete is in a partition and if your data file is another partition? So what effect would have the equality delete on? Will it affect all the data files in that partition or all the data files that you have in your Iceberg? And then again, also the sequence number comes in as well. So these are the primary things we have to take care in our mind. What happened if the table isn't partitioned? What happens in that equality delete that comes into a global effect or not? So all these things we have to take care while developing this writer. So this is another benchmark we have with our first beta release of Apache Arrow. So in October 2025, we received a high benchmark, thanks to Ankit, of 300K RPS, which was before that we had in July 46K, and that was quite a major improvement. In 2 months, with our innovation team working very well, we have achieved a benchmark of 577K RPS in December, which is rows per second, along with quite a good memory utilization. We have sync the NYC taxi data with 4 billion records. You can check on our website how actually we are performing the benchmarks and how we are comparing with other tools in the market. So yeah, thank you so much. Thank you so much for everyone who have tried us out. And if you want to try us out, we are an open source Golang project. You can definitely go to our repo, and we have the Docker Compose and the Helm chart up there as well. So you can simply spin up a Docker Compose or use the Helm chart to use our project. I will hand over the mic to Ankit. He has a question for you all to ask. Thank you so much.
So everyone, if there are any questions, you can ask. And we have one question. If you want Oleg goodies, you can go on the Slack and answer it on the questionnaire channel. This question says that you have different partitions, let's say, and you are writing data like your partition is based on the hour, and you are writing data in equality delete format, and you are using soft deletes basically, where you are not deleting actually, you are just adding one more record there. So what will happen, let's say, when data is coming in the hour 1 and you are updating data in the hour 2? So there are 3 options are given. You can answer it in the Slack and get the first 3 people will be getting the Oleg goodies. So yeah. And also there are pamphlets, guys. Sandeep is here who has the pamphlets. You can contact him about like getting all the information that we have shared here. Yeah. Thank you. Okay. Thank you. If your QR code is not working, you can go to the website. There is a Slack link directly. I guess there is some glitch from the Slack side. Just check on the website. There is a Slack link directly. You can check out. If I'm sharing here, I can also show it. You can directly join from here. Also, here you can see the questionnaire where you can post your answers. Yes. Thank you. Any questions anyone have? Also, they can connect with us, like if anyone have any questions. And we are really active on Slack. Like we get good feedback from our customers which we are using from the production. We are very really active on the Slack. You can post question and you will get answer in like quick time. Yeah, thank you.
Thank you so much, Ankit and Badal. Great talk. I would request now Vishal and Hemant from Google to present the next talk of today. Thank you.
Yeah. Hey, everyone. I am Hemant, and today I'm with my colleague Vishal to talk about Iceberg offering in Dataproc and the Lightning Engine capabilities. So before jumping on, I'll just quickly take a minute to introduce ourselves. Vishal has been actively involved with the big data community, and it's been a couple of years now. He is experienced in Hive, Hadoop, and advancing Spark BigQuery connector. And recently, he has started working on Iceberg sort of things. Regarding me, I have been involved with big data world during since my Cloudera days back then in 2021. And recently, I have moved to Google, in which I am working on the Iceberg side of optimizations. Moving on. These are the key takeaways from today's presentation. First of all, we'll talk about the overview, what the Dataproc exactly is, why do we need high performance compute in today's world, and what is Lightning Engine. And after that, we'll we'll deep dive into Lightning Engine and what are the different stacks that was previously mentioned also. The first is catalog, query optimizer, execution engine, and the IO improvements. And the third, we'll also discuss the gaps that we have identified and the potential areas of improvements. And finally, we'll conclude the presentation. Yeah, so most of you might already be aware of what Dataproc is, but for those who don't know, it's highly managed and highly scalable service to run the OSS applications like Spark, Hadoop, Hive, Iceberg, Delta Lake, etc., etc. It's highly flexible in the sense that customers have the option to submit the jobs in two ways. Either they can create the cluster, they submit the job, and they will be paid according to the cluster uptime. The second option is they can just submit the Spark job and they don't need to create the cluster. And this is in the form of serverless batches. So they will be paid according to the total job uptime. So this is pay as you use strategy. And also this is completely compatible with open source softwares and there is no lock-in involved. Like the customers who are planning to migrate from open source or some other cloud vendor, it's very seamless and continuous experience for them. We also have support for the enterprise grade security. And for that, we are using IAM policies. For the fine-grained access control, we have support for Kerberos-based authentication. And we can definitely control who can do what on the cluster. The encryption of data is also supported in both REST as in and also the in transit. We do have integration with other Google Cloud services like Vertex AI, BigQuery, and Dataplex Universal Catalog. And this is a great solution if you want to integrate the AI/ML workloads. Moving on. So the major question is, why exactly do we need high performance compute? So as we know in today's world, like every device is connected to internet and we are emitting tremendous amount of data. So if I just talk about 2025, the data is growing at a scale of 30% year on year, which is very, very high. So what do we exactly do with this kind of data? So companies generally use it to enhance the customer experience or through the targeted ads. I'll just share the case study of Netflix, which is popular video streaming service. They are collecting data through they are collecting massive amount of data through billions of user interactions. They are capturing every click, every streaming timeline, and also the viewing habits across diverse devices. So they are using this data to run the analysis on this data, and they also tune their recommendation engine and the content strategy accordingly. So with this big data, we need to make sure that we are focusing on the high performance compute, because linearly scaling with the traditional compute is financially unsustainable for most of the companies. And that's why we need high performance compute. The second key aspect is efficiency is the new currency. If we have faster processing, that means less compute hours, that means less cloud bills, and ultimately reduced amount of carbon footprints. So this is environmental friendly also. The major point here is like the traditional legacy JVM based engines that we have like Spark, they are not able to fully leverage the hardware capabilities. So we want to make sure that we squeeze every core that is available to us. And that's when the companies have started exploring native. So native execution unblocks the full potential of CPU via vectorization and the SIMD instruction. We'll talk about it in detail in the upcoming slides. So yeah, just wanted to share the Data Lakehouse market trend also. This is a research by Grandview Research. This is an independent organization, and they have collected the market share of Data Lakehouse functionalities. And currently in 2025, the total market share of Data Lakehouse stands at 13.9 US billion dollars. And it is still growing at 23%, which is very, very high. So coming to Lightning Engine, this is Google's solution for high performance compute. This is new processing engine built specifically for the Spark workloads. It significantly boosts the data analytics and Lakehouse workloads. And also this delivers superior price performance as compared to the standard offering that we had. If I talk about the performance numbers, this is 4.3%, 4.3 times more efficient than the standard Spark that we have. So these are different stacks we wanted to invest on. So when we planned to build Lightning earlier, our primary goal was to improve price performance. But as we went ahead, we realized that optimizing just a single dimension was not at all enough and scalable. To truly move the needle, we had to look across the stack from all the way to like catalog to IO layer and identify bottlenecks at every stage. So therefore, we applied targeted strategies at every level of the stack to unlock maximum efficiency. Moving on, this is a catalog which is the basis of Data Lakehouse. Lightning Engine leverages BigQuery Iceberg REST catalog that has unified view of the Lakehouse. There are a couple of features associated with it. The primary is it uses the open APIs for interoperability. It supports it, and it has support with the multiple OSS and third-party engines through Iceberg REST catalog. And we have integrations with BigQuery, Spark, Flink, etc. And it is built on serverless infrastructure, and it is backed by Google Spanner so that it automatically scales with the data growth. And also we have enhanced governance for this, due to which lineage and data quality is possible through Dataplex Universal Catalog. We also have support for credential vending. So this implements a unique security mechanism that authorizes access at the catalog level. So we don't have to specifically allow users and engines to the underlying cloud storage buckets. And also for this particular case, we are leveraging GCS file IO that has the optimizations for the catalog to storage interactions so that we also make the IO calls optimally. Coming to Query Optimizer, I'll request Vishal to talk about it.
Thanks, Hemant. So as we move across the stack, we'll see what targeted optimizations we had to do across each of these layers. So I'll just briefly talk about optimizers for those of us who don't spend their day-to-day on engine internals. So the query optimizer is essentially the planner of the system. So when you write your SQL query or your Spark data frame transformation, under the hood, the optimizer is what tells the system what exactly to do and how to do it. So the optimizer's job is to figure out how to get this data as efficiently as possible. So it takes your high level code, it breaks it down into a series of physical steps, like, scan the file, filter the rows, and then do the aggregation, etc. or join two tables. And its primary goal is to minimize the cost, which in data lake context, it can mean reducing IO, minimizing the amount of shuffle, or using as little CPU as possible. So why this matters for Lightning Engine is we are focusing on price performance. So even if you have the fastest engine in the world, it cannot really fix a bad plan. If the plan tells you to read, terabytes of data, the engine is going to go ahead and do that. So you've already lost half the performance battle there. So our enhancements focus on making the plan narrower using every piece of metadata that is available so that we can make sure we touch only the data that is absolutely necessary to get the final result. So in the next slide, I'll just go over a few of the targeted optimizations that we have figured in this layer. So the first one I want to go over is the optimized Bloom filters. So Spark does natively support Bloom filters, but you need to have accurate, up-to-date statistics, which is usually an overhead to compute. So during the listing call itself, the advanced optimizer is able to extract the necessary statistics and generate Bloom filters in the plan wherever needed. So then we can use these fresh stats itself to power these Bloom filters. Next, we have the advanced infer filters. So often when you write SQL queries, you have certain hidden filters that aren't explicit in your code, but they can be figured out from the join conditions or even filters that you have put on other tables. So our optimizer automatically finds these hidden constraints and then pushes them as close to the storage layer as possible. So when you catch these filters early, you can prune the data before it ever moves up in the pipeline. And dynamic infiltering. So this is where you have a small side of a join and you can use it to filter a larger table. So usually you have this kind of thing when you're doing a join on a dimension and a fact table and the join is on a partition key, but we are able to extend this to a general column that you're joining on. So we are able to construct a filter and then use this filter to prune row groups inside your Parquet or ORC files. So instead of reading the whole file from the larger table, you're able to filter it in before the processing step itself. And this drastically cuts down on the IO and memory usage. We have also done a lot of more improvements. For example, for Iceberg itself, we have done improvements in the merge space to substantially reduce the amount of processing and shuffle required. So by combining all these smart planning steps, we ensure that the engine only handles the absolute minimum amount of data. Coming to the execution engine. So while the optimizer is responsible for building the plan, the engine is responsible for doing like the actual processing of data, like the low level operations, reading blocks from storage, doing the joins, aggregations. So in standard Spark, this will usually happen on your JVM. In Lightning Engine, we have shifted this entire layer to the native execution model. So looking into this in more details, for years, Spark execution has been mainly limited by the inherent overheads of JVM. So while processing large-scale data sets, JVM spends a lot of significant resources on object management, garbage collection, and even today, Spark is based on a row-by-row based execution. So that prevents it from fully utilizing the performance capabilities that modern CPUs are capable of today. So with Lightning Engine, we are able to avoid these JVM bottlenecks and we are able to leverage native instruction sets. So how we do this is we leverage Gluten and Velox, which are two open source components. So the actual processing of data is moved outside of Java into native C++. So Gluten acts as the bridge. It takes your Spark plan, it converts it into something called substrate plan. And this substrate plan is understood by Velox, which is the library that is doing the actual work. So by doing this, we are able to surpass JVM bottlenecks and move the heavy duty parts of the query to the native layer. So the biggest advantage here is vectorized execution. So instead of processing data one row at a time, we are able to process large blocks of data at once using modern CPU instructions. So this is much faster. It uses the CPU more efficiently. And essentially with the same amount of cores, you're able to get more work done. So some of the improvements we have done over the open source is memory management. So usually when you use Gluten and Velox open source, you constantly have to tune the on-heap memory, which is the JVM memory that Spark uses, and off-heap memory. And you will constantly run into out-of-memory errors. So Lightning Engine is able to use unified memory management. So what we have done is we have made it capable of dynamically shifting memory across the on-heap and native side as needed. So this means you get more stable jobs, and it saves you from the manual tuning of this additional off-heap memory sizing. Next, also, when you use Lightning Engine, you get an engine that is specifically tuned to fully leverage Google's hardware. It can leverage modern native instruction sets like AVX 512, and it can perform SIMD operations. So we are bypassing the JVM layer, and we are also making the engine capable of getting the maximum out of Google's hardware. Next, we have also expanded the support for the Spark operators and functions. Our goal is that when you take your existing code, you should be able to run it on native without doing a lot of changes. So we've also focused our performance efforts where it matters most. So from our analysis, we found that 60 to 70% of time in most queries is spent on aggregates and joins. So by optimizing these operations in native, we've made the most common bottlenecks more efficient so that you get native speed on the queries that you're already running. Also, we are actively working to address gaps in the current native implementation for Iceberg, like DML, write, etc. So coming to the next layer, the execution layer, the focus is on how Lightning Engine handles the resource intensive phases like moving around and transforming data across the cluster, like shuffle operations. So here what we have is we have optimized the serializer and deserializer used by Spark. So we have made this much more efficient so that now it requires a lot less memory and processing. Next, the Lightning Engine is able to leverage columnar shuffle. We have done a lot of improvements there also so that it can use better serialization, deserialization, and also minimize the amount of data it has to shuffle across the network. For Lakehouse specific improvements, we have made the maintenance jobs like compaction and snapshot aspiration more efficient by improving the planning process and also dynamically figuring out the optimal configurations at runtime. So there are a lot more improvements that we have done in this layer. Coming to IO improvements. So even when you have the most efficient native engine, you can still get bottlenecked on how fast you are able to read or ingest data. So if the engine is moving faster than the storage interface, your CPU will mostly be sitting idle waiting for the data. So in Lightning Engine, we have also focused on removing most of these bottlenecks by re-engineering the path from storage to execution. So here we have enhanced the cloud storage connectivity. So Lightning Engine enhances your connectivity to Google Cloud Storage. So it minimizes the amount of metadata operations you need to reduce the number of calls you're making to GCS. We have also integrated with GCS Analytics Core. This is a library we have recently open sourced to Iceberg as well. So now GCS File IO can also leverage some of these improvements that we have done in this layer. Next, on the Parquet layer as well, we have built a specialized Parquet parser, which is able to do prefetching and advanced filtering to reduce the number of row groups that it needs to read. And also it reduces the amount of redundant metadata calls that you will normally be doing with open source Parquet. So I'll invite Hemant to talk about some of the gaps and opportunities that we are currently working on improving.
So these are a couple of gaps and the potential areas of improvement that we are planning to incorporate in the coming few cycles. The first is the merge operation, which is very critical DML operation. We identified 3 main problems with this. There are a couple of more as well, but these 3 are the critical ones. First is it is processing a huge amount of unwanted data in joins that we want to avoid. And the second problem is the amount of data that is being read and ultimately shuffled. This is also very, very high, resulting in wastage of the CPU cycles. And third is it is reading all the columns, even though very fewer are required. The second is the table maintenance operation, which is compaction that we want to improve. Upon investigation, there are like three major problems with this as well. First of all, it works like it doesn't leverage the full capability of the cluster if it runs with the default configuration. So we have to manually tune it. The second is it requires the serialization and deserialization even for the basic jobs that can be avoided. And the third is like the number of compaction jobs that are triggered. Those are very large. So these are few of the areas of improvement that we are planning to address. So this is all, and thanks folks for listening.
Awesome. We are good then. Thank you so much for the great talk. Thanks. With that, we'll move to our last talk for today, but not least. I would request Akshat to come and present the talk.
So hi everyone, I'm Akshat. I'm a product manager here at Cloudera. For the Open Data Lakehouse, I manage everything related to Iceberg and things around that. So before getting into product, I was a engineer and I was contributor to Apache Hive. I've recently authored a book for migration to Iceberg for dummies. So without wasting any time, let me just dive into the agenda for today. So today, what we'll basically try to do is understand the fundamentals of catalog, right? So in every presentation, there was some sort of flavors of catalog and what catalog is used for and all those things. But we'll dive a little bit deeper into it on how these things work and give you a demo also on what Cloudera has done from catalog perspective, right? So I always think that any Iceberg meetup cannot happen without this diagram. So Iceberg, as you know, right, has three different layers. The first on the top is catalog layer, and which is going to be which is the deep dive for this session. And then we have metadata layer and data layer, which I'll skip because we have talked a lot already about it, and there were great presentations about it. So when we see Iceberg catalog, right, what is the purpose and function of it? It's very simple, right? How can any consumer get access to that table, right? Or the data that you have. So catalog maintains that current metadata pointer that basically gives access to any query engine, Python or anything, right? Which wants to connect and read your data in Iceberg. Now, what catalog really stores? So each table has some level of metadata, not just catalog, be it your performance optimization stats and all those things. Catalog can easily store for your engine to do those planning much faster, right? And then there is catalog backends. So catalog in itself is just a service on top of your RDBMS. It can be even file sets, right? In terms of Hadoop catalog, if you can maintain your metadata on top of your file sets. You have Hive HMS as your backend database, and then you have Nessie also, right, with Demio build. So going forward and talk about what Iceberg REST catalog really means. Right? So till then, I think any catalog, if you talk about not just in Iceberg world, but even Hive world, any catalog does the same, right? It maintains the pointer to that table and some metadata. But what really Iceberg REST catalog is, right? So from an Iceberg perspective, it's nothing more than a spec, right? It just tells you a language. It tells you about that, okay, this is the way you build an Iceberg catalog to understand and read those Iceberg tables. So Iceberg have actually given a spec that you can check on. It's an open API spec which you can check what APIs are there, what it is responsible for. So it tells you the language on which you want to build catalog. You can follow them, and you can basically essentially build a catalog in a day, right? But then, why is everyone talking about catalog so much, right? So there must be a key. So that's where every company differentiates in this space and is trying to do something very innovative, right? So catalog space is just flooding right now. So Cloudera has its own REST catalog. Microsoft has OneLake. HMS has catalog. Unity catalog is there. Gravity, Polaris, Nessie, Glue. So many REST catalogs, right? So there must be something that business sees value in, and they're building these things, right? And every company is trying to build their own flavor of REST catalogs or catalogs in general, which basically comes to what we are trying to do, right? So I can talk about what we are trying to do, what problems we are trying to solve, and maybe they can inspire on and share some of the ideas, right? So for us, how we see Iceberg and REST catalog is truly for interoperability, because in today's world, there is no one data platform that any consumer have. So consumers have different vendors, be it Cloudera, be it Confluent, be it Google, whatever, right? So customers have different data platforms, but what they really ask for is how I can manage data in single place and yet give access from everything, right? And that's a problem that Cloudera has been trying to solve. So we see interoperability is via REST catalog, that the problem that we're trying to solve with a unified governance and security layer, right? So that's what we have built for our REST catalog, and it's also open source. You can check out some of the implementations in as part of Hive. We recently launched, and that's what what I'm going to talk about today, right? Cloudera's Iceberg REST catalog, which is GA, and show you how what we have done on the implementation layer, right? So if you remember, we talked about Iceberg giving you the language, right? And every company taking that language and building their own flavors of REST catalog. So this is what we have built. So we as I mentioned, we see interoperability as one of the biggest problems in the space right now. Customers have been asking us that, okay, we use Snowflake, we use Databricks. How can I stay and keep the data where it is while having the flexibility of accessing data through anywhere, right? So the data sharing use case that imagine in today's world, right? If you have two different platforms, one is Snowflake, one is Cloudera, one is Databricks. How do you make sure that, okay, let's say there's a bank, right? Bank has a main branch, and then there is insurance branch, there's cards branch, there is so many others, right? In a bank. Now, how do a bank make sure that every department has the flexibility of choosing their own choice of platform? Because as a bank or as a technology company that everyone is today, wants to give flexibility and availability for innovation, right? So each department wants to have that, okay, no, I don't want to use this platform, I want to use this platform. But as a bank, you need to make sure that whatever you're using or whatever you're enabling your departments to use, you have a single platform where you can manage the governance. You are making sure that whoever is accessing the data is accessing it in a secure way, and there's no issue in governance, right? There's no governance drift in that format. So that's what Iceberg REST catalog is solving. And in the Iceberg ecosystem or Cloudera's ecosystem, this is how it looks like. So Cloudera supports multiple engines for analytics, which is Trino, which is Spark, Impala, Hive, and so on. And then we now, with Iceberg REST catalog, also gives customers the option to support or query from Snowflake, Databricks, and any Iceberg REST client engine. What that means is, with Iceberg gaining more and more popularity, every engine is building their own Iceberg client. That means that they also understand that how do I connect to this catalog and understand and read those Iceberg tables, right? So Iceberg REST catalog truly enables that any Iceberg client. So tomorrow, I think NiFi also has implemented their REST client. So any engine basically can implement this REST client simply and connect to Iceberg REST catalog to access Iceberg data. In the previous world, right, in the HMS world, HMS is built on thrift protocol. So every engine to build that thrift protocol was a little tricky. It was not so easy. The language and implementation takes time. So I think truly that Iceberg REST catalog is solving that problem, right? So I just talked about what we had, but the benefit of the REST catalog is truly the open and agnostic design. That given that it's open source, the APIs are open, anyone can implement their own flavor of this, and it's engine agnostic. Does not matter which engine is trying to read the data from Iceberg. Iceberg REST catalogs tell you that, okay, this is my language, learn it and talk to me, right? You can simply build that, understand that language, and talk to your Iceberg data. It's decoupling the two things, right? So I truly believe what Lakehouse architecture is doing in the modern era of data engineering is decoupling compute from storage. So today in a lot of spaces, you see, if you create a data warehouse, if you want to scale your data, let's say your data is constantly growing, but your query is really not, right? So your compute is not growing, or your data is not growing, but your compute requirements are constantly increasing. So what you really want to do is decouple them, scale these things individually based on what your requirements are. So this allows you to be able to do that scaling. So imagine a customer. So actually, I have a customer story. So imagine you have a customer using 2 different data platforms. Now, you are paying for those 2 different data platforms, and you have data in those 2 places. What you really wanted to do is just use one data platform because it has really great engines, or it has a great user interface, but you want to put everything in one data space, right? So what you can do with Iceberg REST catalog, as I shown before also, right? You can keep everything in one platform, in one Iceberg table, or not one Iceberg table, but one data lakehouse, and then give access to any query engine, right? So it's truly decoupling. So you can scale or scale your compute based on what requirements are, and your data can scale separately. So with that, right, so that's a decoupled simplicity. Then it's secured by design. That means that you can, so every catalog in this space have their own different mechanism of how they are creating governance on top of it, creating security tokens and all. So I can talk about how we are doing it, right? So we have integration with our SDX layer, which is based on top of Knox and Ranger to ensure authentication and authorization, right? So I've talked about this. The topic was about data mesh, right? So I wanted to show where all these things sit in. So from ingestion to consumption. So imagine the 2 major use cases where you have batch data processing and stream data processing. So these 2 are what Cloudera provides. But like, because we are talking more from an open source perspective, you can use anything, right? You can use Spark for this. You can use Flink, NiFi, Kafka directly to dump data into after processing into Iceberg. And this is where Iceberg REST catalog sits in and giving you access to all your data from anywhere, right? So this is generally when you see different platforms, it will always be a vendor lock-in, and you'd have to use the same query engine that the platform supports. So with that, let me talk about, so what I talked about, the core banking use case, right? I'm just going to play a demo quickly of what it looks like. And the example is core banking. So let me just quickly run this video. Okay. So yeah, so as I was talking, let me just, yeah. So as I was talking about that, we have an example of core banking where your banking data or bank is using Cloudera as a vendor, right? So what we're going to show you is how you can ingest this. So basically the end-to-end pipeline, right? From ingestion to consumption from different query engines. And on the background of all of this is Iceberg REST catalog. So what you do is you simply write a query to ingest the data. So there is a very simple query to ingest the data. And let me just fast forward this to a better speed, and I can, yeah. So you see, we are ingesting data. So this ingestion is very simple. Right now, we are giving example with Hue, but you can see the same sort of ingestions being performed by Spark and NiFi or whatever to Iceberg. This is just to show you that, okay, the ingestion is successful. So once you ingest your data into one Iceberg table or multiple Iceberg tables, and so you can see the data is ingested, but this is truly the architecture of the use case, that you have a bank provider, a parent bank, and then different business branches. This is not a new use case. Data sharing has been there from ages, and there have been different ways how you do data sharing or give data access. But this is one of the primary use case, which previously everyone had to create a copy of that data. In many cases today also, we see customers actually downloading some of the, they request data from the platform team create some sort of CSVs and then download them and actually physically give those files to them, right? But with Iceberg REST catalog, you make that job very easy, right? You just give them the access with proper tokens so that they can access that data. So what you're really doing is you're telling the consumer that, okay, I know who you are, you registered with my catalog, and now I will give you security tokens, the JWT token, access token, and secrets for you to access the data. So now you see the UI has changed. So this is the Snowflake UI, right? That you can see. So what you're doing essentially is accessing Cloudera data sitting in Cloudera's Lakehouse and accessing it via Snowflake. So this, what in real will represent is data being accessed from anywhere by different Iceberg engines, right? So let me just, oh, sorry. I just moved a little fast. So if you see, you're basically creating a view of that table and then running the same select query on the table that you created in Cloudera's data platform, right? So there's no vendor lock-in on which where you're accessing the data. And then let me just quickly fast forward it. Yeah, so then let's say there's another consumer. So we talked about Snowflake as being the consumer, right? Then the same concept applies to any other Iceberg engine. We are showing an example of Athena. Okay, I'm really sorry for this. It's just. Yeah, so you see the Athena UI where you're running the same select query and making the data available there as well. So that's the true capability of Iceberg REST Catalog. And so if you're interested in, I think a lot of hands were raised when Dipankar also asked how many people have already been using Iceberg. But if you are interested in understanding Iceberg and migrating to Iceberg and modernizing your data platform, we recently actually published a book on how to migrate from Iceberg. We talked about Iceberg Basic, how the consumption patterns on Iceberg works, how you can actually plan your migration. Either it's zero copy migrations. I was just talking to Rohan as well. And we're talking about how customers require a zero downtime migration. So we talked about zero downtime migration in there and overall business strategy as well on how your platform owners can decide, okay, this is the time for me to move to Iceberg. So we talked all about that in our book as well. So I think I'm making good time. So I'll open up the question floor for questions if you guys have any. I hope it was not so fast. Okay.
Hi.
Hi.
So is it this, I mean, the concept that you talked about, is it any different from, let's say, in Snowflake Federation, Catalog Federation, or in the Databricks Catalog Federation? Is it the concept remains the same or is it any different?
So federation is different than direct access, right? So when you talk about federation, you're truly talking about two services talking each other and sharing that metadata, right? So this is direct access. So when we talk about Iceberg REST Catalog, there's no need for federation. You just get, so for example, let's say if I want to share some data with you, there are two ways. Either I can do a catalog federation where Snowflake can understand my catalog and then federate the metadata from here. So there's a lot of nuances that gets added to it because then you'll also have to worry about syncing that data, right? Imagine you're syncing or federating a catalog in HMS, which is in a different platform. So every time your query engine is going to Snowflake catalog and telling that, okay, I need data sitting in, let's say, any other platform, Databricks, right? For example. And so what it really needs to do, it needs to go to that catalog needs to get the federate data from this catalog, then return it back to the query. So there is a lot of latency added to it and a lot of nuances also because there's sync issues and all those things. It's not an unsolvable problem. It's just a different use case. So federation requires a different use case. And what we are trying to do is a direct access. So if, let's say, you want our platform, what you just really need is to register. You will get a token security to token and you can directly get access, right? So that's those are two different use cases.
Yeah, so one follow-up question. With the federation, we also get capability of data governance in the sense of restricting data who can access. So with the help of this REST API, how is that the security token is there that ensures the security, that is the authentication. But what about
authorization?
Authorization. What about the authentication?
Exactly. So as I talked about, like the security and governance is included in the rest. So I'll talk a little bit about how we are doing it, right? So you have so how Cloudera is doing it is we have Ranger, right? So the authentication is done via the Knox token. So all these token mechanism, you authenticate all those things. And then we have authorizer that makes sure that, okay, so now let's say Akshat is trying to access data for table A. So the REST catalog, when gets the token, first says that, okay, is Akshat even, so let me authenticate Akshat, right? Then does Akshat have access to this table? Or, okay, let's say that Akshat has access to this table. Then there is also comes a point of storage vending, because what we are talking about in all this is just catalog layer, right? Catalog is just metadata. But now that you have metadata, how do you make sure that your engine is accessing only those files that's supposed to be? That's when credential vending comes in, right? So for example, AWS has its token mechanism. So all of that is managed by the REST catalog. And those authentication, authorization, there are different pieces in each REST catalog, depends on the implementation, as I was saying, right? So Iceberg REST APIs tells you the language, and then implementation is up to you. How do you want to integrate governance on top of it? So Polaris has its own governance model. Other catalogs have its own. So every catalog can build their own governance model, but it's all part of this catalog. Thank you for the question.
Thank you.
Any other question? Awesome.
Awesome. Thank you so much, Akshat. Well on time. Now we'll move ahead for the quiz of today. So you can answer, and you need to raise the hand first and then answer the question so that we can give whoever is, randomly will choose or something like that. So we'll give the t-shirts sponsored by Cloudera.
So guys, I'll just lay down the rules. I'll just start the game and read out the questions for you. And whoever can answer it, you need to just be fast and raise your hands. And we need to select people. Whoever is going to be the fastest, they can answer and we can verify if the answers are correct. And therefore, they will receive their t-shirt. So that's how we are going to go ahead. So let's start. Just give me a second. Okay, we are going in. So the first question is concurrency control. What concurrency control method? Which one?
Snapshot.
Okay. What's the answer? I think that. Okay. Yeah. Okay.
MVCC.
No. But this is not how it's done. I think this person was raising the hand. Yeah. Okay.
Yes, the correct answer is OCC.
What's your name? Vedant. Okay.
Many congratulations,
Great.
Vedant.
Congratulations. Moving on to the second one. I think this person.
Yes, that's correct.
Yep. What's your name? Vinit. Congratulations, Vinit. Be faster, guys. Okay, that person. Yeah, he just raised the hand. This is not how it's done. Sorry, we need to pass.
Compaction.
That's wrong. He's saying
This person. Orange.
To read faster, you get indexing.
No.
Partitioning.
All the options are gone.
Clustering.
Yeah. All the options are gone that way. Congratulations, you have been lucky. What's your name? Shivam. Be fast, guys. That green person. Green shirt. What's the answer? Yep. Nope. Nope. No, you have already gotten one, right? No. You didn't get the t-shirt? Samriddhi here as well. We are. Yeah. He was raising his hand.
Who?
Okay. That girl. No, it's not the one. This is just a great guess then. No.
Not a catalog, it's not manifest. Who else?
This person. Who? What's your name? Tejas, congratulations, Tejas. Be fast, guys. And this time you need to be correct in the first go. There's a question about streaming ingestion. I think in the back.
CDC.
Yeah. This one is the most, I guess, easiest one. And I'm sad Oleg people didn't answer this. Okay, sixth question. Second last question. No, she has already answered, no? No, she was wrong. Yeah.
Min-max?
Yes, you're correct. What's her name, please? Pratibha, congratulations. Last question for the evening. Governance and metadata.
Registry.
Sorry?
Registry.
No. Samriddhi here as well.
Catalog.
Yeah, sorry. All the winners, you can please just go there as well. We can distribute the t-shirts very easily. It's all done. Thank you. Oh, thank you so much, guys. Now it's time for vote of thanks. I'm handing over to Samriddhi for that.
Please don't leave, stay. So we did this event in collaboration with Oleg by DataZip. So I would request them to come and share some words about that. So please call your team here.
Shubham, Rohan, Sandeep, Ankit, Badal, and the team, please come over here. Yeah. I will just ask Shubham to share something about our company, and feel free to ask any questions if you have.
Hey everybody, this is Shubham. I'm one of the co-founders and CTO here at Oleg. So we have been creating this product called Oleg. But first of all, let me thank Cloudera team a lot. They have been an amazing host, and thank you for arranging and make all the arrangements with. Yeah. And apart from that, so a quick introduction about me. I have been a data engineer for last 10 years. I've worked with multiple companies in India and abroad. And till the point, till last December or November, when we started developing Oleg, I was creating another data platform. And then we realized that every company on the planet in next 5 years would be on Iceberg. So me, along with my other co-founders, we decided to help people to adopt Iceberg. Right, that's where we started Oleg. So first problem, after talking to hundreds of people, we realized is people are still struggling to get their data into Iceberg. That's a primary P0. Right. So that's where we started Oleg, and our aim was to create the best and the fastest open source ingestion tool on the planet. And that's and the benchmark says the story. But overall, we have gotten 1,300 stars in last 1 year. We have gotten almost 35 odd companies trying us out, using us in production. And overall, the community has grown from almost 470 members in Slack. And also we have gotten 30 amazing contributors on our open source project. So definitely do check us out. Give us a star if you like the project. It's free to try. We have both Helm and the Docker Compose as well. And I would like to thank Ankit and Badal for their amazing contributions around the Arrow and the great presentation. Right. And also, it was really good to listen to Dipankar and, Akshat from the Cloudera team as well as the Google team's presentation. So thank you, everybody. Thank you for attending this event. Yeah.
Just one bit as well. I would like to thank Samriddhi over here. She has been such a supportive member, and we could not have done this event, if it wasn't for her. So thank you so much, Samriddhi.